Hello again. Uh, Here with probability lesson number 3. This one covers a couple concepts that were in each of the last two at some point. But getting in a little more detail here because not disjoint is one of the formulas on your formula sheet for the AP exam, and not being independent is another one of the formulas. And so I want to cover those in some more detail here, and how you might utilize those uh, as we move forward. Um, so first of all, when events are not disjoint, number one, this is, like I said here, you can see the arrow to the formula on the left has to do with that formula. What you're really thinking when I say think Venn diagram here is the overlap of two events. Okay, so um, when you're looking at disjoint and not disjoint, you're thinking about somebody who is in 12th grade and somebody who's in choir. Okay, there are students who are in choir who aren't in 12th grade. There are students in 12th grade who are not in choir, but then there's the overlap. And so that has to come into play. And what you're seeing in this formula, and you can see it here, is that sort of U is a logic symbol for or. Okay, so this is or, and then this is and. So the upside down version is a logic symbol for and. So those would read as or and and in general what you'll see is or is kind of an addition subtraction sort of thing, and is going to be a multiplication division sort of thing. Okay, so what you'll see here is the or statement, a lot of addition and subtraction, even though the and shows up within that formula here, obviously right here. So that's a formula, and what we're looking at here is the probability of, say, being in 12th grade or in choir, okay, is the probability of being in 12th plus the probability of being in choir, but then you have to subtract the group that you just counted twice. So this would be the probability of being in 12th and choir. Okay, so that group, again, we're subtracting them because we counted them in the first group with the 12th graders, and we counted them in the second group with the choir students. And so we are subtracting the students we counted twice there, essentially. And you'll see that a little more here in a bit. So here's an example. Jim has a 50% chance of being accepted at college. Okay, so the probability that Jim gets accepted is 50%. Okay, probability that Sarah gets accepted is 60%. Okay, so we're already seeing the fact that these two add up to more than 100%. Probability that both get accepted, so Jim, and Sarah get accepted is 35%. Okay, so what is the probability of Jim or Sarah being accepted? And again, I don't, not the exclusive or means at least one of them. Okay, so now we see this formula down here. It's this formula in action that we're looking at. So the question is really asking here, what's the probability that Jim or Sarah gets accepted? Which would be the probability that Jim gets accepted plus the probability that Sarah gets accepted minus the probability that Jim and Sarah get accepted. So we know that Jim has a 50% chance of being accepted. We know that Sarah has a 60% chance of being accepted. And we subtract the overlap there of the 35%, which is both of them being accepted. So the chances that at least one of them are accepted, you can see it would be 110 minus 35. Okay, so that would give you 75%. And so that would be our answer here would be there's a 75% chance that at least one of them gets accepted. Okay, we know it's 35 that both get accepted. We now know that it's 25 that neither would get accepted, but 75% gives you the or. And again, this is we can't just add them up, because if we just add them up, we'd stop right there, and there'd be a 110% chance that one of them gets accepted to college, and that, of course, does not make sense. Only professional athletes can hit that number. So we subtract that overlap, and there we have 75%. Okay, now on the independent side, what's happening if they're not independent? Oh, by the way, on the disjoint piece, you'll see that more when we get to two-way tables as well. We'll have some more statements in two-way tables, so that won't be the end of that concept. what if events are not independent now on this one here? So what I've done is I've taken the formula that we have on our formula sheet and I've simply rearranged it. If you recall, this looks a little bit like what we had in our last lesson when we were talking about independence. Again, if they are independent, then the probability of A and B is just the probability of B times the probability of A. And I switched the letters around here just to match um, what they have on the bottom in the formula here. So that's why it's B and then A given B rather than the other way. Um, and so this is what it would look like if they are truly independent. Now, if they're not independent, then we have to say it's the probability of the first event happening, which is B. Okay. So this is our first event, times the probability of the second event happening, given that the first occurred. Okay. So in that situation here, so having B occur first did affect the probability of A, so we can't rely on B and A just being what it was before. So if they're not independent, we can't just rely on this formula, okay, because we know that the occurrence of the first event did influence the probability of the second event occurring. And an example of that here is like picking up cards out of a deck without replacement. Okay, and this without replacement there is the key. Because what we're saying then is the probability that you'd pick a red card out of a deck is really, when you start, 26 out of 52. But now the probability that we pick a red, given that we've already picked a red, of course, is only 25 out of 51. So there's an idea without replacement, that's where this formula, where we have to think about the first event happening when we know they aren't independent already. So we know that we aren't going to be able to use this formula. And I will say that this one is way more common to use when you're actually getting some values than this one, because there's just not a lot of events in the world that are truly independent, at least when you look at the big picture. There's no doubt that that things like flipping a coin and rolling a die are a big spectrum of events in terms of and with replacement with playing cards, but a lot of events, the occurrence of one thing does influence another. So let's get into this a little more. So here we have a um, a two-way table again, and in this two-way table what you'll see is we've got one variable up here is age groups, okay, and one variable is marital status, okay, and not surprisingly, these events, I think I'm not giving anything away saying these are not independent events, that younger folks tend to not be in the widowed or divorced group as often yet, as you'd see in the 65 and over. So these are events that are not independent, and but I want to look at some probabilities with these events. So first one here is probability that somebody is 18 to 24. Okay, so 18 to 24 here in this one would be, and they're technically in thousands of people, but we'll just we'll leave it as just 12,614 over 99,585. So we'll just look at it as being 12,614 people and 99,585 rather than that times 1,000. And now if we look at divorced given 18 to 24. So when we look at this, we think about, oh, sorry about that. We think about this in terms of our formula, okay? So our formula here was A given B in this formula down here, okay? And so I'm going to say that divorced is A and 18 to 24 is B, just for the sake of keeping that straight for future reference. So divorced, given that you are 18 to 24. So given that you're 18 to 24, so now the 12,614 is in the denominator, and divorced in that group is 260. Okay, so that's 260. Okay, then finally, 18 to 24 and divorced. So this would be the B and A now. So 18 to 24 and divorced would be 260, okay, out of the full 99,585. 585. All right, so when you look at these fractions now with respect to this formula that we had over here, okay, so our formula looked like this. Let's take a look at what this looks like now when we put everything in together. So this would be saying now that 260 out of 12, 614 equals, right? Because that would be our A given B. So that's on the left side of the formula. The numerator now is probability of A and B. That was this bottom one. So that's 260 out of 99, 585. So that's our numerator. Okay, I'll make this a blue fraction bar in the middle just to separate that out a little bit. And then our denominator is just the probability of B, which probability of B in this case was just the top one, this one here. So that's 12, 614 over 99, 585. Well, if you divide fractions, you flip the bottom fraction up and you multiply, but what it amounts to is the denominators just get squashed out. So you get 260 out of 12, 614 here, and these two sides equal each other. So that's just all I'm showing you here is how that formula would work with a two-way table and how it does end up working with a little algebra involved. Okay, now setting up the formula here for never married given 65 plus. So, of course, the quick and easy way here to see this would be the idea of just using the table. If we just use the table, we can see that this should be, given that you're 65 plus, well, there's 18,262 who are 65 plus. Okay, and the numerator there would be the never married group, and the never married group is 768. Okay, so this is what we should end up getting. And again, if we have the table, go ahead and use the table. That's absolutely fine. But if we don't have the table and we're just given this in a sentence, then we need to start having the ability to actually use or employ the formula here to figure things out. So the numerator here would be, if we look at what the numerator would be for A and B, that would be never married, probability of never married, and 65 plus. Again, the and means that we just go to the never married and 65 plus, and we take the 768 over the total, which is 99,585. Okay, so that would be our numerator. The denominator here would be just B, and B is again denoted here as the second one, which is the 65 plus. And so the probability that somebody's 65 plus is 18,262 out of the total. Again, we always use 99,585 as the total unless we have a conditional like we did in this first part in the left side of the formula here, where we had the conditional that changed our denominator. But as you can see, now we squash out the denominators again, and we get 768 out of 18,262, which is exactly what we were supposed to get. So again, that's setting up the formula. This is a situation where we know they aren't independent. We know that your age does influence your marital status, but and so that formula gets put to use. Okay, just a couple of other conditional scenarios here to end us. So here we have one where Johnny Chan, who was a World Series of Poker player from my childhood, or shortly thereafter, who made a cameo on TV at least, or actually made a cameo in the movie Rounders. Great movie, you should go see that sometime. Matt Damon. So Johnny Chan needs 2 diamonds to make his flush in the World Series of Poker finale. And there are 3 diamonds amongst the 5 cards face up on the table or already in his hand. Now, I understand that there's cards in other people's hands as well, but right now we don't know what those cards are, presuming that we can't just read the looks on their faces. And so what we know is when we have this deck to begin with, there's 13 diamonds out of 52 cards. But we see that there's 3 diamonds face up out of the 5 cards that are face up total. So that means 10 out of the 47 cards left are diamonds. So Johnny Chan needs to know what the chances are that the next 2 cards will be diamonds. Well, that would mean that we would need a diamond and a diamond, okay, as the next 2 cards. And what that would look like then is that would be the probability that the next card is a diamond, okay, times, again, that's the and turns into multiplication here, times the probability that the second card is a diamond, but again, that's given that we already selected one diamond the first time around. So the probability that the next card is a diamond, as we saw here, there are 10 diamonds out of 47 cards left. Okay, so that would be this. And then if we got that diamond, well, then there'd only be 46 cards left, and there'd only be 9 diamonds left. So this would be 9 out of 46. Okay, so that would give us 90 over 2162, which is approximately about 4.2% or about 4.16%. So again, in this situation, in terms of as a poker player going all in, when you have a 4% chance of hitting your big hand here, probably a no-go, but this is an example of conditional probability. This could also be written as a tree diagram, where we look at, and we'll talk about these more later, but diamond and no diamond, sorry, up at the top again here now. And this is 10 out of 47, and this is 37 out of 47. Okay, and then you got diamond or no diamond, and this one we don't really care about since we already didn't get a diamond, but we could do that as well. And this is our 9 out of 46, so that's the scenario we're looking at right here, is a diamond and a diamond. Okay, and tree diagrams are for back-to-back successive events that we're seeing here, but that's what we have here. Probability that the next card's a diamond, and then times the probability that the card after that would be a diamond, given that the first one was. So that's one more calculation. And the last one here. Okay, so really quickly, of the only 5% of male high school basketball, baseball, or football players play at the college level. We're going to call that A. Of those, 1.7% enter major league professional sports, call that B. And about 40% of these athletes compete for more than 3 years in the pros, call that C. So the question is, what is the probability that a high school athlete competes in college and then goes on to a 4+ year career, pro career? So what we have here is we're looking at what are the chances of getting A and B and C. Okay, so that equals the probability of A times the probability of B given A, which is what I just gave you because I said of these. Okay, so this is probability of B given A, because it's not 1.7% of everybody makes professional sports. It's 1.7% of the high school players who played in college. Okay, now the 40% here again is this is C given A and B. Okay, so that's the third thing. Probability of C given A and B. So this is just an extra round of conditional here. Again, 40% of, it's not 40% of all people who play more than 3 years in the pros, it's 40% of those who have entered the pros. Okay, so again, this is and events. Okay, so and events which lead to the multiplication. And then we just have these ongoing conditionals. So this just is, as you can see now, there's going to be the 5% who go to college times the 0.017 or 1.7% who go on to the pros times the 40% who actually go more than 3 years in the pros. And so when you multiply all those up, you get a whopping 0.00034, which is tenths, hundredths, thousandths, 10,000, 100,000. So about 34 in 100,000 high school athletes go on to have a 4+ year career in professional sports. And of course, this does not include people who don't play at the college level, since it's all that. For those who want to nitpick on the example, thanks a lot. But this would then equal the probability of A and B and C, which was the original question. So again, these are just more conditional probabilities. We'll leave it at that for now and follow up with another lesson here on tree diagrams. Thank you.